Hello everybody, welcome to your introduction to lab number 9, Modified Atwood's Machine or Conservation of Energy Part 2. As a little reminder, we've actually seen this system before in lab 6, Force and Acceleration, where we used Newton's second law to predict the acceleration of the system, and then from the acceleration, we predicted how long it would take to travel a known distance. Well, we're going to look at the system again, and we're going to do sort of 3 different analyses. So just as a reminder, a modified Atwood machine is basically a mass, in this case the wireless cart, attached to another hanging mass passing over a massless frictionless pulley, and when the system is released from rest, the hanging mass will accelerate downwards, the wireless cart will accelerate to the right, and what I'm going to do is use capstone, and I'm going to basically measure for 10 different trials what is the speed of the object, in this case the wireless cart, after it has traveled a certain distance. And what we're going to do is look at, does the work done on the cart by all external forces equal the change in kinetic energy of the cart? We're also going to look at the cart and the mass as one system and look at whether or not the initial energy of the system, which is just gravitational potential energy of the hanging mass, equals the final energy of the system, which will be the kinetic energy of the cart and the mass combined. And just as a review, the first part, we're going to look at, does the theoretical acceleration match the acceleration we get from the experiment? Does the theoretical tension match the acceleration that we get from the experiment? So what I'm going to do is use capstone to basically measure a few different things. One, I'm going to give you the average acceleration of the system, in this case the cart, over all 10 trials, the average tension acting on the cart over all 10 trials, and what is the final speed if I let this system go after 10 trials. So let me just quickly give you a little bit of background, and then let's get back to this, and then talk about the exact analysis. So in our system, or in our experiment, we're basically having the wireless cart, which I'm calling M2, which has a mass of 252 grams. It is on a horizontal, quote-unquote, frictionless surface. It is connected to a hanging mass, which has a total mass of 25 grams, which passes over a massless frictionless pulley. And when I release this system from rest, M2 is going to move to the right a certain distance, our displacement delta x. M1 is going to move down that exact same distance, and then we're going to look at this system a few different ways. So one, as I said before, we looked at this system in lab 6. You used the sum of the forces equals ma to predict the theoretical acceleration. From the acceleration, you predicted how long in seconds it would take to travel a certain distance. Well, what you're going to do here for the first part is, one, you're going to apply Newton's second law to solve for the theoretical acceleration and the tension. So if I look, there's only 3 forces acting on M2. I've got tension to the right, I've got the normal force straight up, and I've got gravity straight down. And if I look at M1, the hanging mass, I have tension acting straight up, and I've got gravity M1G acting straight down. So in this system, since I'm assuming the pulley is massless and frictionless, the tension is the same all throughout the string. Let me remind you, you use Newton's second law to predict that the acceleration, the theoretical acceleration, was M1G over M1 plus M2. This was the acceleration of the wireless cart to the right and the acceleration of the hanging mass straight down. Once you know what the theoretical acceleration is, then you can use Newton's second law to figure out what is the theoretical tension. So the first part of this lab is you are using Newton's second law to calculate what is the theoretical tension and the theoretical acceleration. And both of these are going to be just in terms of M1, M2, and G. And then I'm going to give you the average value of the acceleration over all 10 trials. And I'm going to give you the average value of the tension over all 10 trials. You're just going to do a simple percent difference. What is the difference between theoretical acceleration and experimental acceleration? What is the percent difference between the theoretical tension and the experimental tension? So I'm going to give you from the video what the values are for the acceleration, averaged over all 10 trials. What is the tension, averaged over all 10 trials? Second thing we're going to look at, I'm kind of calling this part 2, is we're going to define our system as just the cart. Just the cart. Which means that if I look, there's 3 forces acting on the cart. I've got basically, like I said before, the normal force, tension, and mg. Since my system is just the cart, that means that my external forces are going to be the normal force, tension, and gravity. Well, what we're looking at is, does the work done by all external forces on the system equal the change in energy of the system? Again, we're not looking at interactions right now for part 2, so I'm not looking at gravitational potential energy. The Earth is not part of my system. So the external forces acting on the cart, the normal force, gravity, and tension. So what we're looking at is, does the work done by all external forces equal the change in kinetic energy plus the change in thermal energy? Well, we're going to ignore air resistance and friction. So we're going to assume it's just kinetic energy that's changing. And so the work done by all external forces is the work done by the normal force plus the work done by tension plus the work done by gravity. Well, since the displacement is horizontal and the normal force acts perpendicular to the displacement, so does gravity. Normal force and normal force and gravity are not doing any work. Since this cart starts from rest, the initial kinetic energy is 0. So the work done by all external forces, which is the work done by the normal force plus the work done by tension plus the work done by gravity, ends up being equal to just the work done by tension. And the change in energy of the system is just equal to the final kinetic energy of the cart, which is our system, because it starts from rest and there is no thermal energy being generated because there is no friction or air resistance. So ultimately what we're looking at is, does the work done by tension equal the change in kinetic energy of the cart? Well, remember, for any constant force, work is just the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. So for tension, our work is the tension, which I will give you the value of, times the displacement, which I'll give you the value of also, but let me just tell you it's 65 centimeters, times the angle between the tension and the displacement, which is 0 degrees. So does the work done by tension equal the final kinetic energy of the wireless cart? So what we're going to do is look at that. Does the work done on the system, which is just the cart, equal the change in energy of the cart? The only work done in the cart is just the work done by tension. The only form of energy of the cart that's changing is kinetic energy. So we're going to call the work done by tension, we're going to call that our theoretical energy, because basically that's the energy that we're inputting to the system, which is just that wireless cart. And how much the system's energy changes should just be the final kinetic energy of the cart. Since it started from rest, we're going to call that our experimental energy. So from the video, I'm going to give you what the tension is averaged over 10 trials, what the displacement is, so you can calculate the work done by tension. We're going to call that our theoretical energy. And then I'm going to give you the final speed of the moving wireless cart for 10 trials. So for each of those 10 trials, you're going to calculate the final kinetic energy. Then you're going to have 10 different energies. You're going to get the average, the standard deviation, and the standard error. And then basically answer, is our theoretical and experimental energies consistent? And again, our test for consistency is, does our theoretical value that we're testing fall within 2 standard errors of our mean value? So you're going to have 10 different kinetic energies. You're going to get an average, a standard deviation, and a standard error. and see whether our theoretical energy, which is the work done by tension, falls within 2 standard errors of our mean value. Third part of this lab, and again, the data is all the same, we're just analyzing it a different way. Now we're going to consider our system to be the cart, the hanging mass, the string, and the earth. And now that the earth is part of our system, I can incorporate gravitational potential energy. Now, if my system is the hanging mass, the cart, the string, and the earth, the only external force is the normal force. But just like before, the normal force is not doing any work. Since there's no work done by external forces, the total energy of the system shouldn't change. So what we're really looking at is, does the final energy of the system equal the initial energy? Now, our big giant equation for chapter 10 is the work done by all external forces equals the change in energy of the system. And we're looking at kinetic energy, gravitational potential energy, elastic potential energy, and thermal energy. Well, we're ignoring air resistance and friction, so no thermal energy. There's no spring in the problem, so no elastic potential energy. So it's just kinetic and potential. The work done by external forces is 0, so the energy of the system shouldn't change. So the change in kinetic energy of the system plus the change in potential energy should be 0. Or if I write this another way, the kinetic plus potential at the end should equal the kinetic plus potential at the beginning. Well, this cart and hanging mass are both starting from rest, so they have no kinetic energy to begin with. And the cart ends up at the ground where I'm defining y equals 0, so it doesn't have any potential energy to end with. And so in essence, we're looking at, does the final kinetic energy of the system, which is the cart and the mass, we're assuming the earth doesn't move very much, and does that equal the initial kinetic energy, the initial gravitational potential energy of the hanging mass? So what we're going to compare is the initial potential energy of the hanging mass, m1g times y initial. How does this compare to the final energy, in this case the final kinetic energy of the moving cart and the moving hanging mass? And again, we're going to call our theoretical energy to begin with the gravitational potential energy of the hanging mass, mgy, and our experimental energy we're going to call our final energy of the system, which is the moving cart and the moving mass. So again, you're going to have a theoretical energy. This will be the same for all 10 trials. The mass is always starting at a height of 65 centimeters and falling 65 centimeters. You're going to have 10 different speeds for 10 different trials. Now, since the cart and mass are connected, they're both moving at the same speed. So whatever speed you get from capstone is the speed of both the wireless cart and the hanging mass. So again, you're going to answer whether or not your theoretical and experimental energies are consistent by looking at, does the theoretical energy fall within 2 standard errors of our average energy? Okay, so let me just quickly touch on the math again, and then I'll say exactly what you need to turn in for the informal report. So part 1, you're solving this system using Newton's second law. You're applying Newton's second law to the wireless cart and to the hanging mass. You're going to get a theoretical acceleration and a theoretical tension. These are both going to be in terms of m1, m2, and g. And then you're going to see, does your theoretical acceleration and theoretical tension, how well do they compare to the experimental values that you get from the experiment? Part 2, we're assuming our system is just the wireless cart. Our external forces are tension, the normal force, and gravity. And what we're looking at is, does the work done by all external forces equal the change in energy of the wireless cart? The only force that's doing work is tension, because gravity is not doing any work and the normal force is not doing any work. So the work done by tension should result in the total energy changing. We're only looking at kinetic and thermal. Since there is no air resistance or friction, there's no thermal energy generated. And since we started from rest, my initial kinetic energy is 0. So what you're looking at is, does the work done by tension, which we're calling our theoretical energy. How does that compare to the total energy of the moving wireless cart? And the only form of energy that's changing in this case is kinetic energy, 1/2 mv final squared. And then part 3, looking at the exact same 10 trials, but now we're analyzing it, looking at our system as the cart, hanging mass, string, and earth. Since the earth is part of my system, I can incorporate gravitational potential energy. The only external force is the normal force, which isn't doing any work. So our equation is the work done by all external forces equals the change in the total energy of the system. Well, there is no spring, so I don't have to worry about elastic potential energy. We're ignoring air resistance and friction, so there is no thermal energy. So the work done by external forces is just the work done by the normal force, and the normal force is not doing any work. And then my change in kinetic energy and change in potential energy. If I move all terms of final energies to one side, what I have is my final kinetic plus my final gravitational potential equals my initial kinetic plus my initial gravitational potential. Well, the system started at rest, so my initial kinetic energy is 0, and I'm defining y equals 0 to be at the level, ground level. So up here, I'm defining basically y equals 0 to be at the ground. So mass M1 is starting at an initial height of 65 centimeters, 0.65 meters. That's how much gravitational potential energy it has, is mgy, where y is 0.65 meters and the mass is 25 grams. Then I let this system go. M1 decreases in elevation, so it's losing potential energy, but the whole system is gaining kinetic energy. So what we're looking at is, does the final kinetic energy of the system, which is the kinetic energy of both the moving wireless cart and the hanging mass, equal the initial potential energy of the system, which is just the potential energy of the hanging mass. So we're calling our theoretical energy the initial potential energy of the hanging mass, and our experimental energy the final kinetic energy of the system, which is both the moving mass and the moving wireless cart. Okay, so in terms of the write-up, try to keep this fairly simple. Here's what you're going to be turning in. Is part 1, which is sort of just redoing an analysis we kind of did in lab 6. Draw a free body diagram of all the forces acting on the wireless cart, which I'm calling M2, and the hanging mass, which is M1, assuming there's no friction, no air resistance. Apply Newton's second law and derive a theoretical equation for the acceleration and the tension, and they're just going to be in terms of M1, M2, and G. Given the values of the masses we're using, come up with an actual number. What is an acceleration theoretical in meters per second squared? What is theoretical tension in newtons? Then I'm going to give you the experimental acceleration and the the experimental tensions just from the results of lab. You're going to compare them to the compare them to the theoretical values using a percent difference. Part 2, what you're going to do is, 1, calculate the work done by tension. I give you the value of tension in the experiment. I give you the displacement over which tension acts, so you can calculate the work done by tension. We're going to call this our theoretical energy. And that's not going to change, right? We're always doing the same amount of work because tension is the same, displacement is the same. At least I'm giving you the average values. So you're going to have a theoretical energy. So then part 4 is, now I'm giving you from the experiment 10 different final speeds for the 10 different trials. For each one, you're going to calculate the final kinetic energy of the wireless cart. Now, you're not calculating an average speed. For each speed, you're calculating a final kinetic energy. And then from your 10 different kinetic energies, you're getting an average, a standard deviation, and a standard error. And then ultimately answering, is our experimental energy, which is the final kinetic energy of the cart, is it consistent with our theoretical energy, which we're calling the work done by tension? And then answering, what are some possible reasons for any discrepancies? Again, our test for consistency, does the theoretical value fall within 2 standard errors of our mean value? And then part 3, again, there's no new data taking. It's still the same 10 trials, but now we are looking at it where our system is the wireless cart and the hanging mass. So what you can do for step 6, just calculate what is the initial potential energy of the wireless cart hanging mass system. We're going to call that our theoretical energy. And we're basically just looking at the gravitational potential energy of the hanging mass, which is m1g(y1). Now, we don't need to consider the gravitational potential energy of the moving wireless cart because it's not changing elevation at all. It's not changing its gravitational potential energy. So again, from the same 10 different trials, you've got 10 different speeds, but now what you're doing is calculating the final energy of the system. We're calling this our experimental energy, but keep in mind it's the kinetic energy of both the wireless cart and the hanging mass. So our experimental energy is going to be the energy of the hanging mass plus the energy of the moving cart. They're both connected together, so they have the exact same speeds. So those 10 different speeds for the 10 different trials is the speed of both the wireless cart and the hanging mass. And then finally, step 8, answering, is our theoretical energy consistent with our experimental energy? So you've got 10 different final kinetic energies. Take the average, the standard deviation, and the standard error. See whether our theoretical energy, which is the initial potential energy of the hanging mass, if that falls within 2 standard errors of our average energy. And again, finally answering what are some possible reasons for any discrepancy. So 3 parts, relatively simple. This is what I'd like to see turned in. Part 1, draw a free body diagram, solve for the acceleration and the tension theoretically in terms of M1, M2, and G, and then compare the theoretical tension to the experimental, theoretical acceleration to the experimental using a % difference. Part 2, you're looking at, does the work done on the wireless cart equal the change in energy of the wireless cart? Cart started at rest, so the only form of energy that's changing is kinetic, so the total energy should be the final kinetic energy at the end. And the input to the system is the work done on the cart. So we're looking at, does the work on the cart equal the final kinetic energy of the cart? And then last but not least, part 3, same 10 trials, but now we're looking at our system as the wireless cart plus the hanging mass. System starts from rest, but the hanging mass has gravitational potential energy. The initial energy of the system, that I'm calling the theoretical energy, is just the potential energy of the hanging mass. Then you let it go. The hanging mass decreases in gravitational potential energy, but the cart's moving, the hanging mass is moving. So how much potential energy the hanging mass loses should all turn into kinetic energy of the hanging mass and the wireless cart. Whew! Okay, that is the introduction and the informal lab guidelines. The second video I have posted is all about the experiment itself. That's it. Happy Wednesday.